Here are solutions to quiz number 3 for ECE 321. Now the first problem looks at a filter. If the input's a constant and a sine wave, what's the output? So here we use superposition. What superposition says, if I have a function of two terms, f of a plus b, that's equal to f of a plus f of b. So treat that this way. I've got two terms, a and b. One's at DC, one's at 5 radians per second. Find the output separately, add them together, get the total output. So starting out at DC, x equals 10. This is the gain everywhere. All I care about is what's the frequency associated with x equals 10, which is s equals 0. Plug it in, I get 142. Now let's look at what's the output when the input is 5 cosine 5t plus 14 sine 5t. In that case, s is j omega, s is j5, x is 5 minus j14, real part's cosine minus j is sine. This is the gain everywhere. Analyze at s equals j5 times the input of j5 gives the output. Real part's cosine minus j is sine. Add the two together, I get the total output. Problem 2. Here's a filter. Find the transfer function. Basically find the poles. So this is a 3-stage RC filter. Due to increasing R by 10 times, roughly there's no loading. So one pole is at 1 over RC. That gives you 100. 1 over RC gives you 20. 1 over RC gives you 0.714. So at this point to here, the DC gain is 1. The gain is 1 plus the ratio. So it'll be 1 plus 200 over 100k gives you 3. So that'd be the transfer function. Written as we write it in controls, poles at 100, 20, 0.7, DC gain 3. In communications, they write it this way. Same thing, just different way of writing it. In controls, I like it because you can see where the poles are. In communication, you can still see the poles, but you can also see the DC gain. So either way is valid. Number 3, if I use positive feedback, I get complex poles. One pole, here's the real pole, is at 1 over RC. That gives a pole at 71. This 1 over RC gives the complex pole. This is, the correction today is 14. This is 71, 1 over RC. Here 1 over RC is 20. The gain K is 1 plus the ratio. K is 2.5. So for the complex poles, the pole's at 20. K is 2.5. Solve for the angle, and I get 75 degrees. So here's the transfer function. Pole at 71, pole at 20 at 75 degrees, and its complex conjugate. Problem 4. Give the transfer function of a filter that passes frequencies below 80 radians per second, rejects frequencies above 110. And by reject, I mean the gain is less than 0.2. First, determine how many poles you need. That'd be as you go from 80 to 110, with n poles, the gain drops down to 0.2. Solve for n is 5.05. Meaning I need at least 6 poles. I could use a Butterworth, Chebychev. Chebychev works better. And pick the corner between 80 and 110. If you had MATLAB, you could adjust it to get it fine-tuned. But a first guess is let's put the corner at 80. So this is a Butterworth filter, 6 poles at 80 radians per second, corner at 80. This is a Chebychev filter, 6 poles, corner at 80 radians per second. And come what they look like, a Butterworth filter, all poles have the same magnitude. Scatter 7 or 6 poles in the left half plane. The Chebychev filter is an ellipse. Take the Butterworth filter and squish it down, and you get a Chebychev filter. Problem 5. Give the transfer function for a 7th order Butterworth filter with a corner at 100. The angle between the poles is 25 degrees, 180 over 7. So I have a pole here, being odd number, one pole is at the real axis, up 25 degrees, up another 25 degrees, up another 25 degrees, and the complex conjugate. So there's the transfer function. And finally, here's a filter. Find R's and C's to implement this filter. The first one, 1 over RC is 72. If R is 100K, C is 138 nanofarads. For the angle to be 38 degrees, I get 3 minus k is 2 times the cosine of the angle, giving you k is 1.43. So this would be 435. And I didn't realize this when I made it. These are different. They weren't supposed to be. It's not a trick. So if you use 1k, it's 435 ohms. Or if you just said 100k, 100k, 43.5k. On a gain of 1.43. The second stage pulls at 111. So R is 100k, solve for C2. C2 is 90 nanofarads. Angle is 77.8 degrees, and that gives you 3 minus k is 2 cosine of the angle. Solve for k, I get a gain of 2.57. So R2 is 1.57 times R1 times this resistor, 157k. The total DC gain is the gain of the first stage, 1.43, times the gain of the second stage, 2.57, 3.68, 3.69. So that's quiz number 3 for ECE 321.